Okay, we're just going to, as quickly as I can write, fill out this front organizer sheet, and then we'll move into some details. So first thing we want to do is observe a phenomenon. I do not write the best with this pen, but hopefully it helps me pace better so I don't get too far ahead of you guys while you're working on your notes. Develop a question. Following the question, we want to develop a hypothesis. Experiment. Move this up. Which will lead us to data collection and analysis from our experiment, from which we will make conclusions. Now, we'll wonder, did it work out or did it not work out? If it worked out, it may be moving toward adding to the body of knowledge leading to a theory. If it didn't, that does not mean we're a failure. That just means we need to try something new. Come up with a new hypothesis, work on a new experiment. Even if it did work out, we have to have further experimentation for it to lead to the theory. So, the scientific process or scientific evaluation consists of 6 interrelated processes. I know you guys are all familiar with this, but of course the first one is observation. That's what we did with the magic box. You notice it seemingly produced more water than was actually possible. So you start to collect data. There are different types of data you can collect, but it's the result of measurement. Measurements or observation. And there are 2 main types of data. One type is qualitative. And if you circle that right there, that might help you remember that qualitative has to do with just a general description, a quality of something. Not exactly measured. It can't really be measured. You can't really measure color, odor, not with your senses anyways, without special equipment. Shape, texture, taste, smell, big or smaller. Those are just some examples. And I have 2 pictures here from my work that I did before I taught. I have some stained soils is a qualitative descriptor, as well as saying there was a sheen on the water and a strong petroleum odor. I didn't have an odor meter measuring that exactly, or something that I could get an exact measurement of the sheen. So those are all qualitative descriptors and qualitative data. Now, quantitative is, again, go on and put a box around that first part, and that should look like the word quantity to you, and that answers the question exactly. It is something that is measured. Exactly how much, how little, fast, slow, big, heavy, the temperature, hot and cold. Some examples of quantitative data I've got here are the feed ratios and amounts for your livestock, the shell load for the most uniform pattern to take down whatever you're hunting. Pharmaceuticals, medicine, obviously, are quantitative data. And if you'll look here, I have a lab report from some samples that I took. Maybe that one that we were looking at, probably that one up there. BTEX, it's some bad stuff, causes cancer. And you see we have an actual result here that is reported with units of milligrams per kilogram. Okay, that is quantitative. We have an actual quantity of benzene that is in the sample, and in this case it's less than the detection level, so that was not a concern. But again, that is quantitative, whereas sheen and stinkiness were qualitative. Our next step in scientific process is to formulate a question. So after you observe something happening, then you formulate a question, which moves you to a hypothesis, which is a proposed reason or answer. A proposed reason or answer for what is observed, that can be tested. That's a big deal there. It has to be tested. Okay, if you're running into something that cannot be tested with a scientific experiment, then it's really not a scientific question. It's not to say it's not valuable, but it's not science, such as testing the existence of God. It's not the same thing as adding to the body of scientific knowledge. Okay, we are making an educated guess, but again, it needs to be able to be something that can be tested. So you'll see I have a blank right below that, right here. Observation of a phenomenon or something you see happening calls for some explanation, and the process of explaining observed behavior, again, begins with a hypothesis. I'm not going to make you write that. If the hypothesis survives extensive testing, it may attain the status of either a theory or a law. So let's talk about that a little bit more. That's going to be important. It shows up on a lot of standardized tests, things like the MCAT and such that you may need to take later in life. So a theory is tested by more experiments and modified if necessary. Modified. My E's I cannot get very well. A theory is considered successful if it can be used to make predictions that are true. Okay. For example, Einstein's theory of relativity or the atomic theory, they explain broad principles of nature and they have been supported over time. But please remember, all theories, this is your next blank, all theories are subject to new, I'm going to abbreviate because I don't have a lot of room, are subject to new experimental data. And they might change. And let's see if I can find some room there. Subject to new experimental data and can change. Now, a law, there's just a little bit of difference there. It actually summarizes the results of many observations and experiments. Such as, if someone skydives from a plane, they will always wind up back on the Earth's surface. You're watching things constantly that fall to the Earth, and you come up with laws of motion from those many, many observations. Your next step is going to be experimentation. They're a carefully designed testing process to reinforce or refute whatever it is you're testing. The model system, theory, or hypothesis. You notice it does not say the word prove. You're not proving, but you're just, if you get a yes, if you get what you expected, then you're adding to the body of knowledge and to support for that. And if you get a no, you are disproving and also helping to add to the body of what we know about that particular topic. So for the results of an experiment to be accepted, anyone must be able to consistently produce the same result by completing the experiment as directed. The same result by completing, and I'm going to put as directed. I'm about out of room there. As directed. Okay. When you're setting up your experiments, you've got to be careful about setting up your variables, and your independent variable is what you can change, what you change in an experiment. Your independent variable should be the only condition that affects the experiment's outcome, and everything else should be identical. And controlled. For example, in an experiment to determine the amount of yeast that will create the fastest rise in dough, the amount of yeast would be the independent variable. Now your dependent variable changes in response to the independent. Changes in response to the independent variable. Okay, so the dependent variable then, looking for the amount of yeast, was your independent variable, and what it does is your dependent variable, and so that's what you're measuring. It's the height. So if you do your if-then statement, if certain amount of yeast, then height. Okay, that if-then can really help you figure out your independent variable. Whatever follows the I is your independent variable, and then whatever follows then is your dependent variable. So in order to know that it is your independent variable causing what you think it's causing, you have to make sure to have good controls. And those are the variables that must stay the same. Must stay the same to eliminate false or misleading results. To eliminate false or misleading results. Okay, so when you're dealing with this bread experiment, we're talking about everything except the amount of yeast has to stay the same. So the flour type and amount, sugar, water temperature, the surface on which it rises, and so on. They must stay the same. To be certain it's just the amount of yeast causing the differences of height. Okay, also during experimentation you have to prevent cross-contamination, which is indirect contamination caused by contact with a contaminated source. Contact with a contaminated source. And it doesn't even have to be a contaminated source. For example, in our bubble experiment, if you had only used one straw, then you would have cross-contaminated all of the solutions by putting the one straw in all of the solutions. So that is something you have to be very careful about. So in an experiment or test, if you do not prevent cross-contamination, like I said, then your results are not valid. The fifth step is after you get your data, you need to analyze it. So you've just experimented, now you're going to analyze what you came up with. You can't just stop at the experiment like a lot of people do seem to want to do. Always think about your results. Always think. Especially in lab situations. Do they make sense? If not, figure out why. Come up with an idea why they are not making sense. What could have happened? Rethink your controls and variables. You've probably just not had a good experimental design. You might have cross-contaminated. Any number of things could have happened. And I have an example here from one of my jobs that I was on. The results showed that there was contamination, even though repeated testing in the past had shown that there was no contamination. So there was an email string where I showed my lab people that this well had been contaminated, even though more than 10 years showed it had never been. And so what actually happened is the lab was contaminated that day, and they went back in their notes on when they took my samples and found out that they had actually cross-contaminated my samples. But if I had just stopped and just accepted it, you know, that could have cost our state, because this was a state contract, that could have cost, you know, $5,000 to $10,000 or more, actually a lot more, because it was showing contamination and we were going to end up having to go in and remediate, and that would cost a lot of money. So always, always question results, and do not be afraid, and don't worry about making someone mad or have to do more work. It's worth it. And then a conclusion you've got to come up with. It's just a judgment based on, based on the information obtained in the experiment. And one way that we can communicate our conclusions often are a model, which is a drawing or a 3D representation of a hypothesis. And I'm going to go down here. I can't, this pen is too thick to write small. Of a hypothesis, theory, or law. You guys did that with the magic box. You came up with your hypothesis and you drew it. Many hypotheses, theories, and laws are expressed with mathematical equations. Those are actually models. That may confuse all but the best of mathematicians. I don't know if anybody watches the show Numbers. It's on Netflix. If you haven't, it's definitely worth watching. But models just simplify complex ideas. That's an L. Sorry, simplify. I've left out the P as well. Let's see if I can erase this. Try again. Simplify. It's late. I can't spell anyways. And provide a visual image. Okay, and I've got some shown below here of just some models to help simplify a complex idea. Okay, that's it for this section. Make sure you've got your notes filled out, and I'll see you when I see you.